For the next couple of video series here, we're going to be taking a look at fluids. So we'll start with fluid statics, which is just plain looking at what happens when a fluid is just sitting there. But to start, we need to define what a fluid is. A fluid is something that, under the influence of external forces, can flow to assume the shape of its container. So it doesn't have to fill the container, so gases and liquids are both examples of fluids. And this definition of fluid can be even maybe a little broader than you might think. Because there's nothing in this definition that says how fast the fluid has to flow. So, for instance, certain kinds of plastics are considered fluids. A good example is the silly putty. Silly putty is actually a fluid. Now, if you get yourself some silly putty and you play with it and you shape it into something, it'll hold that shape. But then if you go and stick it back in its little egg and you let it sit for about a year or so and you come back, you'll find that the silly putty will have flowed to fill the bottom part of the egg. Another example would be the Earth's asthenosphere, which is a layer just under the Earth's crust. It's very, very plasticky. It flows very slowly, but it does flow. And so if you're to wait long enough, it would fill the shape of its container, or assume the shape of its container. Another example of a fluid would be a plasma, for instance, the state of matter that's found in our sun. Their containers get a little tricky. You have to use things like magnetic bottles to contain them. But if you use magnetic bottles, which is just cleverly arranged magnetic fields, you can indeed get it to assume the shape of its container. All right, now there are some things that people tend to think are fluids that aren't. And probably the single biggest example of that would be a glass. Glasses are actually solid, but they differ from conventional solids in that a conventional solid usually exhibits what's called long-range order. So that is, if you look at a little chunk of the solid at a molecular level in one part of the solid, and then you go to a totally different part of the solid and you look at the molecular level, you'll see that the arrangement is basically the same. That's not true for glasses. For glasses, it's true in the immediate neighborhood of wherever you look. If you look nearby, it looks pretty much the same. But if you go far away, the arrangement of molecules will be very different. But it's still a solid, and it won't flow no matter how long you wait. There's a lot of misconception about that, and that has to do with people looking at glass windows from houses that were built in, say, the 19th century. There, what's really at issue, and the reason that they point this out is they say if you look at the windows in houses of that era, and usually what you have is lots of small pieces of glass held together by strips of wood to make a larger opening to look through. If you look at each of these small pieces of glass, you'll typically see that the bottom of the piece of glass is fatter than the top. And people point to that as evidence that the glass is flowing, but it's just taken a very long time. But that's actually incorrect. It turns out it was like that to begin with. It turns out that it's very hard to make a uniform flat sheet of glass, and that's really something that we've only gotten good at as humanity in the 20th century. And so if you go and look at these pieces of glass from earlier, part of the reason why they were small was you couldn't make them big, and there were definitely variations. So when you would cut the pieces of glass to make the little panes, typically one end of it would be thicker than another. And if you're going to put those pieces of glass into the window, it's just natural to put the fatter end down because that felt more stable when you grabbed it and put it in. But you can look around and you can find examples of workers who put them in the other way, and you see the fat end up on the top. That's not saying that the glass is somehow magically flowing upward. It was put in that way. So a lot of what we're seeing is a combination of not as good quality control as we're capable of today, combined with just what naturally feels good. But it is actually the case that a glass is an example of a solid. It doesn't flow no matter how long you wait. All right, now to take this on a little further, treating actual fluids can get a little rough because there are definitely intermolecular forces happening. And so for a starting point, what we would like to do is just pretend they're not, or at least that we can sort of ignore them. So we know that there are intermolecular forces happening, but what we'll do is we'll pretend that what we've got, sort of the image that I always have is like take a Ziploc bag and fill it with, say, like BBs or little marbles or something like that. And you can squish it as much as you like, and the little BBs will move around and they'll stay next to each other. And if you look carefully at the BBs as they move around when you do that, you'll find that they'll swap positions with each other. That's the hallmark of a liquid versus a solid. In a solid, they wouldn't be able to swap positions, but they still tend to stay right nearby each other. So in the real world, this is happening because the molecules are interacting with each other. But for the moment, we'll just think about the interactions insofar as it keeps them near each other and kind of leave it at that. We'll have to extend this definition of ideal fluid later. When things are moving, we'll have to add some additional conditions to that. And so we'll deal with that when we get to that point. Now, before we can move on, I also need to define density. Density is the ratio of an object's mass to its volume. And we're usually interested in it when we're looking at objects that are uniform. So if I look at some small chunk of it, it looks like any other chunk of it. In that case, the density, and this is not a letter P, I'll get into what it is in a second, is defined as the mass of something over its volume. Typical units that physicists will use are kilograms per cubic meter. Okay, now real quick, this letter here that looks like a P but isn't is actually a lowercase Greek letter rho. So if you're to try to draw one, if we go back to the special paper that we all learned to write with, you typically make a rho like that. That's one variant. Although if you make that variant, you got to work very hard to resist turning it into a tadpole. If you have a hard time being able to draw this and telling it apart from a letter P, another common variant that people do is they put a little hooky on, and then they usually draw it more vertically like that. But in either case, you start from the bottom of the letter and you draw up. Alrighty then. So in physics, typical units are going to be mass will be kilograms, volume is typically cubic meters. And just a bit of a warning here, if you've run into density in other contexts, such as chemistry, they tend to use grams per cubic centimeter instead of kilograms per cubic meter. So what this means is that, say, the density of water turns out to be, if it's fresh water, is basically 1,000 kilograms per cubic meter. In fact, this was The earliest definition of the kilogram was based on this. Actually, it's the definition of the gram. So originally the gram was defined as the mass of a cubic centimeter of water. So the density is 1 gram per cubic centimeter. And that was the initial definition. Very quickly, that definition shifted to a definition to the immediately previous definition, which was the mass of a certain blob of metal kept in France, and was only recently superseded by the setting the current definition done in early 2019 of setting the Planck constant to an exact value. So the blob of metal was one of the longest running continuously used definitions. Why did they switch to that blob of metal? Because the goal was to have something that was lab reproducible and water's available everywhere, right? Turns out water's a royal pain to work with. First off, its density fluctuates quite a bit, and it's at its densest at 3.5 degrees C. So they figured that out pretty quick and said, okay, at 3.5 degrees C. That resolved that. But the other thing is that if there were ever to be, the closest thing it'll probably ever find to a universal solvent is water. Water just dissolves and holds things really well. And it turns out it's really hard to make pure water. And that wound up being the actual great technical hurdle, was just the extreme difficulty of making pure water. So the blob of metal in France definition was made to get as close to this ideal density as possible, and only recently superseded by making the Planck constant an exact number. So physicists, though, instead of working in centimeters, grams, and seconds, are called CGS units, we tend to work in kilograms, meters, and seconds, which are called MKS units. So just watching out for your unit conversions here. So it's just an aside, 1 gram per cubic centimeter. If we want to convert this into cubic meters, right, we're going to have kilograms per cubic meter. First thing we have to do is we'll go ahead and convert the kilograms, the grams into kilograms, so we can multiply by 1 kilogram over 1,000 grams. That's good. Now here's the tricky bit, is to remember that for each, that there are 3 powers of centimeter here, and each of them needs to be individually converted into cubic meters. So 100 centimeters over a meter, that takes care of 1 power. Then I need another 100 centimeters per meter. That takes care of the second power. I need another 100 centimeters per meter. That takes care of the third power. So finally, 1, 2, 3 to cancel all of those. And then this cancels nicely, and I am indeed left with kilograms per cubic meter. So what we got? We got 1, 2, 3, 4, 5, 6 zeros on top, 3 zeros on the bottom. So sure enough, I'm left with 1,000 kilograms per cubic meter. So if you've encountered densities in, say, chemistry or some other context where grams per cubic centimeter are used, the real fast way to convert to kilograms per cubic meter is just to times everything by 1,000. Okay, so we've already in a previous video introduced pressure, but just for a quick review, pressure, wow, what is going on with that? There we go. Pressure is defined as the force being exerted on some area over that area. And it's a scalar, it's not a vector. You can make a little pressure gauge. In fact, this is the basis of many pressure gauges, by just having a little piston with a spring in it. The spring will exert a known force. The more it compresses, the greater the force, right? And so the pressure will be the force exerted by the spring over the area of the little piston head. The manufacturer knows what that area is. They know what the spring constant of the spring is. And so they just calibrate. They have a little follower that follows the piston, moves a little gauge around, and you can read the number. There are other designs, but that's one. And if you stick it in a fluid, it turns out it doesn't matter which, so these are supposed to be molecules of the fluid. It turns out it doesn't matter which way you point it. You could point this thing any which way, and it will always read the same value. So again, just by way of review from before, the units of pressure that are used in SI are the Pascal, which is 1 Newton per square meter. This turns out to be a rather small unit of pressure, so atmospheric pressure by means of comparison. Atmospheric is 101,300 pascals, or equivalently 101.3 kilopascals. And I already sang once, but I'll go ahead and do it again. You can remember that as the ident for some hypothetical radio station on the west coast of the United States. 101.3 kPa. So we've seen for when we were talking about gases earlier, we saw that what was our main cause of pressure in a gas was just the fact that the molecules of the gas were moving around randomly and striking up against the walls of the container. And these collisions were exerting our forces. There is a slight gradient. Because of gravity, there will be slightly more gas molecules at the bottom, and the pressure will be a little higher. It'll be a little lower up here. But if it's a gas, unless you're talking like, say, a room or something like that, where you can definitely measure it, it's usually not a big deal. This is different from a liquid, and so we'll be mostly thinking about liquids here at first. Although I will mention, again, gases just briefly before we get there. So with the liquid, I've got my water line here. If I look at some small slab of liquid here, it has to support the weight of all of the fluid above it. So you've got all the fluid above it pushing down on it. You've got all the fluid below it pushing up on it. So the fluid, because the fluid itself has some weight, the fluid underneath is going to have to push up harder than the fluid up above. And if we're, say, looking at a cube of fluid, then the areas involved would be the same. So that means the pressure down here would have to be greater than up here. So as we descend in the fluid, the pressure is going to increase, and we will make that quantitative shortly. Again, in a previous video, I went through all of the other ridiculous units of pressure. I'll go ahead and just refer you to that video. But I will say, if your container of gas is the entire planet, then if you're standing here, what is happening is all the air above you is pushing down on you. And then you, and thankfully all the air around you, is pushing up on that air. So you'll have, if I look at this, all the air above you, you'll have the force of gravity of that air there. You're exerting a normal force there. So again, same deal. As you go further down, the weight of all the air above you increases. And so that means that you'll have to push back up harder to keep that air from falling down. So the forces will go up. That means the pressures also have to go up. All right, so with that, let's go ahead and turn our attention over to liquids for the moment. And we're going to go and take a look at Pascal's law. Yes, the same Pascal as in Pascal's triangle, although he was by no means the first person to come across that. His is just the most recent name to have been attached to it. And yes, he also was very influential in developing the field of probability in order to help settle questions like how to fairly split the pot in a card game when everyone was just getting tired and wanted to go home and they didn't want to finish it out. All right, so with that, let's go and look at a beaker of fluid. Any fluid will do. We can imagine water. That's fine. And so let's think about a cube of water sitting in the water. And again, here we're going to imagine that it's an ideal fluid. So it's our bag of molecules here. So I'm drawing a 2D slice of what's happening in 3D. So we should think of this as a cube going back, but I don't want to clutter the drawing. So let's think about what's happening. We know that right here, the fluid above is pushing down on this surface here. We'll call this surface number 1. And we'll just go ahead and mark its depth right here, like so. And we'll mark this other depth we're interested in as surface number 2. So all the fluid above our cube of fluid is pushing down, and all the fluid underneath has to push up. We'll call that F2. Then now there's also forces that are lateral, but those forces will cancel out. The right and leftward forces have to be the same, otherwise the cube would squish sideways. But F1 and F2 aren't equal. And this is because if we draw a more careful free body diagram over here, we have to remember that the fluid itself has some weight, so there will be a force of gravity on it as well. So we've got our force of gravity down, we've got our force of the fluid due to the fluid above pushing down, F1, and then we'll have to have a bigger F2 pointing up to cancel those out. And then again, there are these lateral forces from the fluid that cancel out because the fluid isn't sliding around. Okay. So with that, we can start to apply Newton's second law here. So we can say F net equals ma. And we're assuming that this is a static situation. The fluid is just sitting there, so the acceleration would be 0. And we'll go ahead, and since the x component isn't all that interesting, we just know that it's being pushed the same all around. We'll look at the y component. So the y component here, we've got F2 pointing up, and then the other two things we got pointing down are F1 and gravity. So this will be minus F1 minus Fg. That has to equal 0. All right, so I'll go ahead and rearrange this to say that this is F2 equals F1 plus Fg. And let's start to take a look at that. So here, by definition of pressure, so at this point right here, we'll mark some pressures here. This point right here, this will be at atmospheric pressure, just for comparison. We'll get to that in a second. Then we'll say right here at depth 1, the pressure at this depth we'll say is P1, and the pressure at this depth is P2. And we know that the pressure has to be the same all the way along, because if it weren't, let's say it were bigger over here on the right, then the force of the fluid on the right would be greater than the force from the fluid on the left, and this cube of fluid would slide around. But we're saying it's not. So we know that anywhere at this depth, the pressures have to be the same. But the pressures don't have to be the same between depths. And we remember our definition of pressure was the force over the area. So we can rework that to say that the force is equal to the pressure times the area. And the area that's going to count here is going to be the area of the top of the cube here, and similarly the area of the bottom of the cube there. And since it's a cube, the areas of all the faces are the same. All right, so we can substitute that in. So my F2 is going to become P2A, and my F1 is going to become P1A, like so. And then the weight of the fluid is just going to be mg. Now, here we need to look at one other tidbit, and that is, remember that the density of a fluid, let me write that back up here, the density of the fluid is its mass over its volume. So I can rewrite the mass as the density times the volume. And another way we can write the volume is to say there'll be this cross-sectional area here times this height right here, h. So we can go ahead and say the volume is AH, so we'll make that substitution there. All right, so if we make that substitution, we'll have we will have, there we go, P2A equals P1A plus rho AHG, and the A's cancel. And so rearranging just very slightly, we are left with P2 equals P1 plus rho GH is the usual way that you will write this. Now, this might give you pause for just a moment, and it should. That rho GH, think for a second and ask yourself, where have I seen an expression that looks like that before? Okay, I'm hoping that you decided that you have seen that before, in that if this were an M instead of a rho, you'd say, hey, this is the potential energy. But this is M over the volume here. So this can absolutely be written as the gravitational potential energy of the fluid up at height 1, up at location 1, which remember is the upper bit here. This can absolutely be viewed as the gravitational potential energy of the fluid here with respect to this height, this location here, per unit volume. This gets a name. It's called the potential energy density. And so we can look at that and say, all right, if we're saying this is a potential energy per unit volume, is there some way we can interpret the pressures as being some sort of energy per unit volume? And it turns out you can, because remember, what's the source of pressure? One of the sources of pressure is the actual movement of the molecules as they collide against other molecules. So it's related to the average kinetic energy of the molecule. So it's proportional to the thermal energy over the volume. So the pressure is proportional to the thermal energy density. So we'll keep that in the back of our mind, that while we got this from doing forces, we can also think about this doing energies. This will be more important in the next series of videos when we get to Bernoulli's equation, when we're looking at moving fluids. I just wanted to point it out now. All right, so we can take this a little further. And we can just say, well, what if I just want to figure out what the pressure is? How could I do that? Well, we can always reference off against some known pressure, like right here. This is basically going to be atmospheric pressure. You're going to have to go up quite a ways, up or down quite a ways, before this changes from anything other than atmospheric pressure. So we can just say, if I want to know the pressure down at that point there, we can look at this depth D here. And then I can rewrite this and say, if we called it the pressure at that depth P, I can rewrite this and say P at that depth is just, the pressure at that depth is just P. And now instead of me picking this height, this reference pressure here, I'll pick this reference pressure here, which is atmospheric pressure, which I know, plus rho times G times this height here, D. So as long as the density of the fluid doesn't change, and it with depth, and in the real world it does change, but for a lot of fluids, such as water, it doesn't change too quickly. So it's usually still good to approximate it as not changing. What we see is that the pressure just goes up uniformly with depth. So to do a bit of a more concrete example with that, and then to talk about and then to follow up with how long can the longest possible straw be. Let's imagine that you are diving in fresh water. So if you've taken diving classes, you may have learned the dive tables for salt water. They are different for fresh water, and this is because the density of the water is different. So let's say you're snorkeling or diving in fresh water, just so because we know the density there. So I'm going to try to draw some goggles. This isn't going to work out very well. I'm going to try to give you a snorkel as well. Okay, I tried. So one of the things you might be interested in is knowing how deep can you go before the pressure becomes equal to 2 atmospheres instead of 1. Well, we can go ahead and follow through with Pascal's law here, and say the pressure will be equal to the atmospheric pressure plus rho times G times the depth. And what we want is the depth here. So let's see, it's going to give me rho GD equals P minus P ATM. Then we can just divide by rho and G. Okay. Now when you do this, you're going to need to be a little careful. And this is because you need to make sure you've got compatible units. So here, don't just go and say 2 ATM minus 1 ATM and call it a day. And this is because when you put in your density, you got 1,000 kilograms per cubic meter and a gravitational field strength of 9.8 newtons per kilogram. All right, small favor there. You have newtons per cubic meter there. You've got atmospheres here. And how the heck are you going to get meters out of that? Well, what you're going to have to do is you're going to have to convert those atmospheres into pascals. So it's 101,300 pascals per 1 ATM. So with that in place, we can go ahead and cancel our ATMs and crunch it through. You will get 10.3. We should probably grind through our units and make sure we're good. So we've got pascals over newtons per cubic meter, but we remember that Pascal is a newton per square meter. So if I go ahead and rationalize my denominator, right, this is going to be newtons per square meter times meters cubed over newtons. Cancel, 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 cancel. Yay, it's meters. Good. So a depth of 10.3 meters. Now, I promised that we'd also talk about the longest possible straw that you could use. And it turns out that the longest possible straw you can use, again, if we're dealing with fresh water, is 10.3 meters high. And this is because the way a straw works is when you put your mouth around the straw here, sorry, I tried. What you're going to do is you're going to make a partial vacuum. Well, the lowest you could ever conceivably make that pressure would be 0. And then the straw is sticking in your beverage or whatever, so the pressure here is going to be 1 atmosphere. So 1 atmosphere minus 0, that's still a difference of 1, just like here. So that means that this maximum height we can have, so the lowest pressure you could possibly make in your mouth is 0, means that this max height is 10.3 meters. And this is something that people discovered kind of the hard way in the Middle Ages, when wells with we'll move that over there. When wells with buckets in them started to get replaced with hand pumps. Hand pump works on the same idea. It causes a partial vacuum to be made, but they found that no matter how clever they got in designing the pumps, they could only lift water 10.3 meters. This was a problem in some parts of Europe where the water table was deeper than 10.3 meters. And you can actually find drawings in some settlements where you can see that people dug pits down, say maybe 8 or 9 meters, stuck a pump down there, and then some poor person would have to take a ladder or staircase down, run that pump to fill up a bucket, and then there would be another pump whose pipe ran into that bucket, and their buddy 8 or 9 meters up above would pump it again. And so by tag teaming it, they could lift the water more than 10.3 meters. So what do we do about that today? Turns out that if you have to sink a depth more than 10.3 meters, the line that's going down to bring up the water also has an air pressure line going down. And so it's called a jet. And so what you do is you pressurize the water in the immediate vicinity so as to increase the differential pressure so that you can lift the water more than 10.3 meters. Alrighty. So that will segue into technologies for measuring pressure. So we'll start with a barometer because that's basically our straw. Come on, there we go. So we'll start with a barometer. This is a device that measures what's called absolute pressure, which is the only kind of pressure we've been looking at so far. And the way that this was originally developed by Torricelli, I totally cannot recommend that you do now because I don't want you to get heavy metal poisoning. But what Torricelli did was he basically filled a bowl with mercury, and then he filled a very long test tube with mercury. And then he flipped the test tube upside down and let the column of mercury seek its own level. Why mercury? It's because it's a metal that happens to be in the liquid phase at temperatures where humans are actually willing to hang around. And because it's a metal, it's very dense. So instead of 10.3 meters of water to have a pressure difference of 1 atmosphere, it turns out that 760 millimeters of mercury will do the trick. This takes it from being something that you have to build a multi-story contraption for to something that you can fit nicely on a wall. So anyway, when the mercury seeks its own level here, other than a few random mercury atoms that happen to be floating around up here, the pressure here is pretty much 0. And then the pressure you're trying to measure will be the pressure right here at the surface of the mercury. So this is the pressure P2 that we want to find, or we'll just call it P. And then what you do is you measure the height of this column of mercury, D. So starting with Pascal's law here, we'll say P2 equals P1 plus rho G D. P1 is just 0, P2 is P, so P equals rho G D, where rho here's the density of the mercury. So this is a measure of absolute pressure, what the pressure is right here. Now, other device, a lot of times, so what we don't really care what the absolute pressure is. We care how it differs with the surrounding pressure, which pressure in the surrounding area, which is usually atmospheric pressure. So to that end, there are a whole collection of different devices that can all be classified as manometers. And these measure what we call gauge pressure. So here, let's say you want to measure the pressure of a sample of gas here. What you might do, but you only care what it is relative to atmospheric pressure. What you might do is you might put like a little U-shaped bit of glassware around like this and fill it with some liquid. This liquid, it could either be mercury or it could be water. Water is actually very popular in engineering application. And then what's going to matter is the difference in the heights of the column here. So we've got this pressure here is P2. This I'm trying to show as being, here, let's do a better job of it. I'm trying to show this as being open to the air right here. So this is going to be my pressure P1. And this is usually, but does not have to be, 1 atmosphere. So again, we can say P2 equals P1 plus rho GH. That's Pascal's law. But now what we're going to do is we're going to measure the gauge pressure, which is going to be P2 minus P1. That's what rho GH measures here. This is what's read on the gauge, thus the clever name gauge pressure. Now, an important thing to keep straight here is absolute pressure can only ever be a positive number, but it is totally possible for gauge pressure to go negative because it's comparing the pressure between, say, the inside of something and the outside of something. So in this case here, what I have in mind is you may be aware of what are called negative pressure buildings or negative pressure rooms. I used to work in a negative pressure building once a long time ago. It was required by chemical hygiene codes because there are certain classes of chemicals that if there's a spill, the concentration at which they kill you is lower than the concentration at which you will smell them. And so then for the safety of everybody, usually the lab in which these chemicals are being used is it will be kept at a negative gauge pressure with respect to the building. And then the building itself will be kept at a negative gauge pressure with respect to the outside world. It doesn't have to be much, which is why it's often measured in inches of water rather than mercury. And the whole idea is if you have a spill, you go ahead, you slam down the hood, and you get the heck out. And when you open up the lab door, air rushes into the lab, not out, hopefully keeping the chemical inside. And then, of course, you're going to have to hit the pull the fire alarm, get everyone to leave. And so as people leave, they go out the building, because the absolute pressure of the building is lower than the surrounding air, the air rushes into the building, not out. So that way, hopefully, when the people with the bunny suits come in to take care of everything, the nasty chemical in question is contained hopefully inside the lab, but at the very least inside the building, and so it doesn't pose a hazard to people. This is also used in infectious disease wards if there's a possibility of some bug having an airborne transmission vector. Sometimes what hospitals will do is they will put the patient in a negative pressure room. Again, that's still a positive absolute pressure because it's impossible for absolute pressure to be less than 0. But what it means is the pressure inside the room is low. The absolute pressure inside the room is lower than the absolute pressure outside the room. So when you look at a manometer, it'll read a negative number. And again, it's the same deal. That way, as the medical staff go in and out of the room where the patient is located, every time they open the door, air rushes in, not out, hopefully keeping the pathogen in the room. So those are a couple applications there. But the manometers are, unless you're using a barometer, the gauge you are using is probably some sort of manometer measuring gauge pressure. For instance, if you are inflating your tires, that again will be gauge pressure, because what matters is how much harder is the air inside the tire trying to push the tire out versus the air outside the tire trying to push it in. It isn't quite so relevant what the absolute pressure inside the tire is, because you're trying to get a certain specific shape, and that's going to matter more on the difference in pressures. So your tire gauge is a manometer. It's just measuring the difference inside the tire versus outside the tire. So I'll finish this off with one other application. This is a contraption called a hydraulic lift. So if you've seen a hydraulic jack as an example of one, and I'm going to draw it badly, but hopefully it'll get the point across. So if you have a hydraulic jack, or hydraulic lift, usually the way these things work is you'll have a piston over here on a very small cylinder wall. And then usually you've even taken a step further and you've rigged up some sort of a lever here so that you push down on the lever to make it easier to push down. And as you push down on the lever, like so, the pressure here is going to go up because you've literally increased the force being applied here, and the area is not changing. So the thing is, remember, the pressure has to be the same at every depth. So that means the pressure is going to go up over here as well. But the area here is much bigger. So you could be pushing down here with maybe 100 pounds of force or something like that. And then over here, you could lift the entire side of a car. Very useful if you're trying to do things like change the tires on the car, do a rotation, something like that. Now you might look at that and ask yourself, wait a minute, am I getting something for nothing here? Because you're saying that the area here is greater, and since the pressure is the same, that means the force this is exerting is greater. And that is absolutely true. Much bigger force over here than over here. But the something for nothing question is a statement about work. So keep in mind that since this is very skinny here, this piston's going to have to move quite a ways to move this guy even a little bit. So usually the idea with a hydraulic jack is you're just trying to barely get the tires to clear off the floor. So you don't have to move this piston very much. You'll have to move that a fair amount. So the work done here and the work done there are the same. Small force, big distance. Big force, small distance. Alrighty. In the next series of videos, we will be taking a look at what happens when we let fluids move. Catch you over there.